All right, I guess we should go ahead and get started, folks. Anybody have any questions before I do so? We obviously had the previous several minutes to do that, but I want to make sure no one else has. I also want to remind everybody to go ahead and chat me your first and last name so we can make use of that for my role, of course. So it looks like no questions. All right.
Oh, sorry. I
Yeah,
just
go
have a
ahead,
quick
John.
question. For the exam, when do you plan on getting this grade? Obviously, no rush, but I was just wondering.
Yeah, I ended up having to do them on paper, so normally I would have them graded the same day. I should have them graded tomorrow though and posted. And the whole purpose of that, of course, one was it makes it easier. I've actually had some students still try to cheat, even though I do a lot of things to lock down the browser and all that stuff. So I did the paper for that. But the other reason is I can now give you partial credit if you get the multiple choice part wrong. So it might take a
Okay.
little longer, but I would definitely say tomorrow or Friday at the latest.
Okay, so yeah, so just basically moving forward, it will be all in paper.
Probably for the face-to-face test. Yeah, just
Okay, sounds
because
good.
yeah, I think I can do a better job for my students in that case.
Okay,
All
sounds
right,
good. Thank you.
no problem. Thanks for asking, John. Were
Yep.
you there today? Did you come see me, or did you go to the testing center?
Yeah, no, I was there. Yep.
Okay, gotcha. Yeah, I
Hmm.
recognize a couple names like Daniel and Taylor and John. So I was curious if I had. All right, well, let's go ahead and get started, folks. We are in chapter 6 on gravity. That brings us up to example 6.3 is the one I'm wanting to work. This is one where you're starting to be able to use a formula that uh, gives you a magnitude of a force, and then you can make that into an actual vector quantity. So it's kind of useful. This question isn't the best for that, but it does do it a little bit. So uh, it's example 6.3. I'm going to go ahead and start it right now. So example 6.3. This is from your book. I'm going to read it out loud. Hopefully, I'll read it slow enough where anybody can follow it, but you can also refer to your book. It says, force on the moon. Find the net force on the moon due to the gravitational attraction of both the Earth and the Sun, assuming they are at right angles to each other, as in figure 6.5. And what they give us on this is the mass of the moon, which I'm going to call M, big M for moon. That is 7.35 times 10 to the 22 kilograms. We have the mass of the Earth, and I'm going to use the symbol I've been teaching you that we use in astronomy for the mass of the Earth, and that's 5.98 times 10 to the 24th kilograms. And then the mass of the Sun, and I'm going to use the astronomy symbol for that. That's a circle with a dot in the middle, and that's 1.99. Oops, 1.99, not 1.96 times 10 to the 30th kilograms. Okay. Now, what we also need, of course, is their distance separation between them. What I want to draw, though, before that is I would like to draw a figure of it, and we're going
Are you
to.
sharing your screen?
I have not yet. Thank you for reminding me of that. I just jumped right in, and
Okay, I just wanted to make sure I wasn't wrong.
no, you're not. Thank you for saving my old senile butt. Here we go. Yeah, yeah, I completely was not sharing. What a crackhead. Oh well. So here we go. I am writing this down. Let me start with a figure just so you'll know we're all on the same page. I'm going to draw a circle down here, and obviously this is not going to be to scale. In fact, it's virtually impossible to draw a scale model of our solar system that includes the sun and our planet. You could do possibly Mercury and Venus, but even then, that's really problematic because Mercury and Venus are so small compared to the distance between them. And even when you start to put the sun in, you can then actually make a observation of the orbit of the moon if it was actually drawn out in space, but the planet itself is an infinitesimal dot. What we're looking at here, though, is a very specific phase of the moon. You could call it first quarter, but it could also be possibly third quarter. I'm going to say the moon is right here, and this should be in perfect line with this. And then off to the right of it is going to be the Earth. And again, like I said, definitely not the scale. Whoa, I just made that an ellipse by accident. So this is definitely not to scale. But there's our circle. What we need, of course, are these distances. I know, for instance, the Earth Moon distance is 3.84 times 10 to the eighth meters. So I'll put right here uh,
Is the 1.99 times 10 to the 30th supposed to be kilograms,
kilograms.
or is that just a K? Okay.
Yeah, I left off the G. I think I got sidetracked in the middle. 3.84 times 10 to the eighth meters is this distance from center to center. The distance from center to center for the Earth or for the Moon and the Sun is about the same as the distance between the center of the Earth and the center of the Sun. So we're going to go with that. That distance is 1.50 times 10 to the 11th meters. And you can find this information, for instance, in the front cover of your book, or if you're using the e-text, you'll look off to the right where it has a table of contents, and that data is in useful references. So if you click on the useful references, you'll see fundamental constants, then units, and then periodic table of elements. That has basically the stuff that I've been putting at the bottom of your electronic tests. So we also know that the formula for gravitational force is F is equal to G M1 M2 over R squared, where M1 and M2 are the masses that are interacting with one another through a gravitational force, and R is the separation distance between their centers of mass if they're physical bodies. And your book talks about this. Newton was able to show basically when he introduced his theory of gravity, he was able to show that with that law of gravity, a spherically distributed charge or mass distribution is going to behave just like a point particle if you put all of its mass at exactly the center of the point particle. So that's another route for us where we don't have to complicate the issues. We can just go from the geometric center of a sphere to the geometric center of a sphere instead of having to go through all the trouble of calculating the center of mass and all that good stuff. So we have all this. Now what we want to do is calculate the total force on, I'll read the question again now that I've got the drawing, but we want to find out the total force acting on the moon. It says find the net force acting on the moon due to gravitational attraction of both the Earth and the Sun, assuming they're at right angles to each other. So, what I'm also going to do is I've listed this, but I want to remind you that forces are vector quantities. So, if I say the total force on the moon, that means the force of gravity on the moon due to the Earth plus the force of gravity on the moon due to the sun. So that's the way I've got to add those. That means I have to go ahead and do that calculation first. But also I want to point out to you that the force between the moon and the earth actually goes to the right. So I will put it right here. This is the force between the moon or force on the moon due to the earth. And then I'm also going to have a force on the moon due to the sun. Now, I drew these sort of haphazardly. In fact, I suspect that that the force sub ME, the force on the moon due to the Earth, is a little bit bigger than the force on the moon due to the sun. But I've drawn them in the opposite direction. But the main thing is when we actually go to compute the vector quantity, we'll have the magnitudes correct and that sort of thing. So let's go ahead and just calculate the magnitudes of these two forces first. So the force on the moon due to the Earth is equal to 6.67 times 10 to the negative 11th. I'm going to leave the units off. You guys should definitely practice putting the units in and paying attention to those units. Right now, I'm just trying to fly through it so that we don't have to spend so much time computing all that. So, in this case, it's G, then times the mass of the moon, and the mass of the moon, of course, is 7.35. Oops, it switched to trying to make a pretty drawing out of everything, so it tried to make my 7.35 into something geometric, and that wasn't good. That's 7.35 times 10 to the 22 kilograms times the mass of the Earth, which is 5.98 times 10 to the 24th. Notice that the mass of the Earth is almost 100 times larger than the mass of the moon. Now, the distance between them we found was 3.84 times 10 to the 8th, and that's meters. And of course, we've got to square that. So that's what we're looking at here. We're going to go ahead and try to compute it. I'll turn on my calculator. 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22 times 5.98 times 10 to the 24. I'm going to go ahead and get that figure. Now I'm going to divide that by 3.84 times 10 to the 8th squared. So I'm going to say divided by, and I'm going to put parentheses about it. I've been finding some fairly decent calculators lately, not keeping the exponent from the from scientific notation, not keeping it with the actual mantissa of the scientific notation when I do a division. So I'm using parentheses probably more often than I should, but it's okay. It doesn't harm you. So I just wanted to let you guys know that might be something your calculator is doing as well. In other words, like when I do, I just finished calculating the product of the G, the mass of the moon and the mass of the Earth, and I got 2.93 times 10 to the 37th. What I did was then did divide by parenthesis, and then I typed in 3.84 times 10 to the ninth. What I've been finding is sometimes, at least a couple calculators appeared to do, basically make that 10 to the eighth multiplied by the numerator instead of the denominator. So I'm putting parentheses around it for that reason. When I do compute this, what I get is, and we actually had three sig figs on everything, so this should be 1.98 8. I always carry one extra sig fig, of course, so 1.988 times 10 to the 20th, and that works out to be newtons, as you can tell, because the G was Newton meters squared per kilogram squared. We multiplied it by kilogram squared, that left Newton meter squared, and then we divide it by meter squared, and that left us with newtons. So we now have the magnitudes 1.988 times 10 to the 20th. Now I also want to do the same thing for the force on the moon due to the sun. Again, that's 6.67 times 10 to the negative 11th. And then I'm multiplying that by the mass of the moon, which is 7.35 times 10 to the 22 kilograms, times now the mass of the sun, which is 1.99 times 10 to the 30th kilograms. And I'm dividing all that by 1.50 times 10 to the 11th meters. That is what we call an astronomical unit, by the way. Now I'll do 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22 times 1.99 times 10 to the 30th. That gives me a 9.755 times 10 to the 42. Now I'm going to divide that by parentheses 1.50 times 10 to the 11th, close parentheses squared, and that gives me 4.33. 6 times 10 to the 20th. And again, this works out to be newtons. It seems like I was actually wrong. It is almost, well, it's a whole factor of two larger. The force on the moon due to the sun is a factor of two larger than the force on the moon due to the Earth. So now we have those magnitudes, and really all we have to do is use our Pythagorean theorem to get the magnitude, and then we use a trig function to find out what the actual angle is. So what I'm going to do is complete the parallelogram since I have these vectors drawn tail to tail. There I am completing my parallelogram. The force is actually going to be like this, and this isn't too terribly off scale. I drew the FMS to be essentially three of those squares uh, long, whereas the FME is only two. So it's a little shorter than it should be. The FME is a little shorter than, excuse me, the FME is a little longer than it should be. What I'm going to do is calculate the angle between, let's say, the force MS. No, I really don't. I don't think that's that relevant. I'm going to calculate this other angle instead. I'm going to call this angle phi. Well, there I am, my stupid program automatically changing it to quote unquote some geometric figures. So what we also have is the F of the total, the FM. The total force on the moon is equal to the sum of the squares of these two because they are at right angles because they set it up that way. This would be 1.998 times 10 to the 30th, or excuse me, times 10 to the 20th. And actually, I was thinking about putting the 10 to the 20th out in front of the square root. That could have been done because it's going to be common to both of them. But anyways, 1.988 times 10 to the 20th squared, and then 4.336. Again, the 6 is not a sig fig either. That's times 10 to the 20th, and that's also going to be squared. And now this is where I've got to be careful about taking the squares and adding them. I know I'm going to get a square root times 10 to the 20th basically, so I'm going to pull that out in front, but I'm going to take the 1.998 and I'm going to square that, and that gives me 3.992. And that's four sig figs, which means there's one figure that's not significant. And now I'm going to take the 4.336. I'm going to square that, and that gives me 18.80. And of course, that was three sig figs. So now I only have three sig figs in that one. So what this shows us is the 18.80 restricts the number of sig figs because the actual decimal place that you have to round to is one decimal place, even though I have two decimal places in the other one. Now, all of this is b times 10 to the 20th, and it'll be in newtons like that. But now that I see that, I can take the 3.992 and add that to the 18.80, and I just have to recognize that that's going to be 22.79, but it's only good up to the 7, so the 22.79, the 9 is not significant, and when you take the square root of that, that means it's the square root of three digits, therefore we get three digits of sig fig. So now I'm going to take the square root of the 22.79, and that gives me 4.77. And then 4, that's the non-significant digit, times 10 to the 20th newtons. That is the total force, Fm. And I'll circle that off. That's the magnitude of that diagonal vector we saw. Now, the other thing we can do is we're going to take phi and recognize that that is the tangent inverse or the arctangent of opposite over adjacent. The opposite is the force on the moon due to the sun, which was the 4.336. Now notice if I put the 10 to the 20th up there, I would have the 10 and the 20th at the top and the 10 to the 20th on the bottom. So they're just going to cancel out. So I'm just going to write it as 1.99, or excuse me, 1.988. I don't have to write the 10 to the 20th because I know it's going to happen anyways. So now I'll take shift arctangent parenthesis 4.336 divided by 1.988 in parentheses. That gives me 65. Now we did do 3 sig figs divided by 3 sig figs, and then we took the trig function of that, and I taught you guys that you're supposed to just whatever numbers sig figs go into the trig function, you work it out with whatever math principles that you are having in the actual parentheses, which in this case was division. I was dividing 3 sig figs by 3 sig figs, so I got 3 sig figs, and then my argument is that if you put 3 sig figs into a trig or a arc trig function, then you should get 3 sig figs out. So that makes this 65.37 with one extra non-significant digit degrees. So that is the angle phi as drawn on it. So you can see that the force, the net force acting on the sun, tends to pull not only the moon a little bit closer towards, or attempting to pull it closer towards the earth and closer towards the sun, but it also pulls it along in an angle in front of that so that it, well, you can see it from the diagram. That's sufficient, I guess. Anybody have any questions on that? All right, so let's move on to the next area, which your book talks about writing Newton's law of gravity in in a vector form. I usually don't do that, but I'm going to do it this time. What I want to do is give you an idea of how we would do that, because this will come in handy and make you start thinking about vectors in general. Normally, I do something just like this in the chapter 21 when we get to 242. And I'm sort of, that's the first time they see anything like it. So I'm thinking it might be better if you see it now and then you'll see it again later. So let's start off with just drawing a coordinate system. And this is just for reference so I can label vectors and things of that sort. But I'm going to call this my x-axis. I'm going to call this my y-axis. I'm going to call this my z-axis. Notice it is a right-handed coordinate system. Again, that means if you hold your right hand like this with your index finger pointing like it's, a gun, and your thumb pointing up like it's the cocking mechanism of a gun, and then your middle finger's pointing as if it could go into the trigger slot for the gun, then what should happen is you should point the X in the direction of your index finger, the Y in the direction of your middle finger, and then the Z has to be in the direction of your thumb. If it's not in that direction, then it's a left-handed coordinate system, and that's going to prove mathematically complicated if you have to do any operations like cross products. So always make your coordinate systems right-handed. Now, what I'm going to do is I'm going to imagine a little blob of mass. Well, actually, let's make it a little less complicated because I already told you the deal with regards to a finite mass. Newton showed us that if that finite mass has spherical symmetry, then we can pretend like it's a point mass with all of its mass right at the geometric center of that sphere. And if it's not a sphere, you can just find the center of mass of that shape, and then the force is going to act along the line connecting the center of mass of one of the masses to the center of mass of the other mass. So that's what gets us a vector component. So I'm going to just treat it like it's a circle of some sort, and that'll be just fine. So what I'm going to do right here is I'm going to say this circle represents mass m1, and I'm going to say this circle right here represents mass m2, And now with that, I'm going to say there's a vector that points from the origin to the mass M1. I'm going to call that vector R1. There's also a vector that points from the origin to the location of mass M2. And again, I'm pointing it to technically the center of mass for M2 and for M1. And this vector is going to be called R2. So what we know is if we made a line that connected the center of mass of M1 and M2, then the force of attraction due to Newton's law of gravity would, in fact, be parallel to that line. So it's just a matter of discussing whether you're talking about the force on M1 or if you're talking about the force on M2. So now what I'm going to do is draw that line that connects the two centers of mass, and I'm going to see if you guys have any idea of what mathematical operation we can do with the vectors R1 and R2 to make a vector that's parallel to that green line. And I don't care if it points from the M2 to the M1 or from the M1 to the M2. I just want to know, do y'all know of some kind of mathematical, algebraic operation between two vectors that would give us specifically a vector that's parallel to that green line? Anyone? Don't feel bad if you don't. Very rarely do I get people that can answer this, but I want to always give you the chance because it's a learning experience. Anyone? Okay, well, it's perfectly normal, especially at this point in the semester, because you haven't necessarily learned a whole lot about vector algebra and vectors in general. But the operations that you can do between two vectors are you can add them, you can subtract them, you can take a dot product of them, which is called a scalar product. That, of course, obviously spits out a scalar instead of a vector, so that's clearly not the one. And then you could also take what's called a cross product, or also called a vector product. That gives a vector that's perpendicular to both of the two vectors that you're operating on. So that would be a vector that's perpendicular to both R1 and R2. So that's not helpful for us either. That means we're left to addition and subtraction, and the answer is subtraction. So for instance, if I wanted the force on M1 due to M2, this is red. Force on M1 due to M2. Okay. The force on M1 due to M2, we know that gravity is always attractive. So what's going to happen is the force on M1 is going to point from M1 towards M2. So I'm going to say the vector we're looking for in this case points this way, and this would be F1, 2, like that. Now, if you remember about how we add vectors, what we used was A minus B is defined to be A plus the opposite of B. So what I would like to do is have a vector that starts on M1 and ends somewhere near M2, or in principle, it could actually land or end at M2, and then it would have the advantage of having its magnitude be equal to the r that we want in the bottom of Newton's law of gravity. So if I look at it that way, then what I could see is, oh, I would like basically R1 to be turned backwards. And then if I turn R1 backwards, that would mean R1 and R2 are head to tail. And the vector sum of those two would be from the new tail of R1, in other words, after you turned it around, from that tail to the head of R2, which is exactly what I want. So what I'm going to do now is imagine over here that there's another vector that goes from here to here, and this little vector is negative R1. So that's what that little green vector is there. And now you can see that R2 plus negative R1 is technically equal to R2 minus R1. And we're going to give that a shorthand name, and that shorthand name is going to be R21. Okay, because it's in the order of subtraction. Since we know the vector that relates the two vectors to get that vector parallel to the force was done by subtraction, and it therefore is always going to be done by subtraction, then writing it as 2 then 1 tells you, oh, I'm doing 2 minus 1. So with that in mind, I can now say the force F12 is equal to G times M1 times M2 divided by, now I'm going to do the magnitude of R21 squared, because it actually does extend all the way from the center of mass of M1 all the way to the center of mass of M2. But now I'm going to multiply that by the vector R21. But when I multiply that by the vector R21, then I'm canceling out one of the magnitudes of R21 down below. What I'd really like to do is, instead of multiplying G M1 M2 over R21 squared by the vector R21, I would like to multiply it by a vector parallel to R21 whose length is 1 unit. So it turns out you can actually make a unit vector by just taking a vector and dividing it by its magnitude. So R21, which we define to be R2 minus R1, can be made into R21 with a hat over it by just taking the vector R21 and dividing it by the magnitude of R21, which is also written as R21 over magnitude R21, like that. So now, if I wish to do that, then instead of me writing what I had here, the R21, I'm going to go ahead and write it as the R21 divided by the magnitude of R21. In this case, it's not squared, it's just 1, because this quantity right here makes R21 hat, the unit vector. So now I actually have a description for F21, and it's not exactly the same the way your book wrote it, because me and your author, textbook author, have a differing of opinions, or differing desires of how we write F21 and R21. Specifically, the R21 is different. He agreed, or he writes the same way I do with regards to the force. But here it is. Finally, it's going to be G times M1 times M2 divided by R21 cubed times R21 vector. So that is the vector force. And you'll notice your book has a similar one, but it has a negative in it. And when it says R12 and R21, I'm trying to double check what it's saying. Okay, so R21 is the vector that points from 2 to 1. And that would mean, yeah, so they're using sort of the opposite notation of R21 that I use. So that's why it's a little different from mine. But the main thing is that you know how to use a particular version, and that you work out well enough that you figure out a particular version you want, and then you can use it. That being said, you rarely have to use that this semester. I mean, you can use it every time. Sometimes it's a waste of time. Other times it's really helpful. But if you don't know how to use it, it's never helpful. So, anyways, that's a way you can actually write out a vector for the force equation, the gravitational force equation, in terms of vectors, where if you just identify what is vector r1, what is vector r2, then you can go ahead and calculate the vector r2 minus r1. Then you can calculate the magnitude of the vector r21, and then you can, of course, cube that and put it in the bottom, and then multiply the whole f equals g m1 m2 over r21 magnitude cubed. You can just multiply that by the vector r21, and boom, you have it. Okay. Anybody have any questions on that? All right. So next, what we want to do is I did want to let you guys know it's not there yet, but in this week's module, there will be two extra credit problems, one of which will be where you can take Newton's law of gravity and the centripetal acceleration formula and Newton's second law of motion. You can combine all those, and going on the assumption that the orbit that a planet would go around, for instance, in going around the sun, or the moon would follow orbit going around a planet. If you go on the assumption that that orbit is actually circular, then you can make an approximation by roughly saying F equals G M1 M2 over, and here I'm going to use the letter A because A is what we represent the semi-major axis with, as I showed you last time. So I would replace the A or the R with A, and I would also use the time required for one orbit, which would be going from here to here. That's going to be a capital T, which is the letter we use for a period. And by doing that, you can substitute in the velocity, which is the circumference divided by the period. And you then have an equation that's only relating G, M1, M2, A, and T. And when you write all that out, you will actually derive Kepler's third law, and you will have a constant in there that I'm also asking you to convince me, in other words, do a unit conversion and show that that constant, which I'll tell you happens to relate to G, the gravitational constant, M, the mass of the sun, 4, and then pi squared. Those are what it matters, or what it depends on. But when you do that calculation, you'll either get, depending on whether you do it one way or the other, you'll either get one astronomical unit squared, or excuse me, cubed over 1 year squared, or you'll get the reciprocal of that. So that's going to be one extra credit problem that'll be at the bottom of this module. And then another one is calculating the acceleration of gravity at the highest place on Earth, which is Mount Everest, and on the place that's closest to the center of the Earth, which would be at the bottom of the Marianas Trench. That's going to require you to Google those heights. Of course, your textbook actually gives you the height of Mount Everest, so it's 29,035 feet. Or if you read the Into Thin Air, you'd probably remember that. It did actually change since that book, by the way. We had an earthquake, and it actually changed. I want to say it was originally 29,026 feet, and it went to 29,035 feet after one major earthquake. So that's kind of neat. But those extra credit points are there. Now, with that being said, let me go ahead and show you how we go about calculating gravitational acceleration on planet Earth, or any other planet for that matter, using Newton's law of gravity. So here it is, gravitational acceleration. Whoa. There it goes again. It automatically changes my writing into something it thinks is geometric. So gravitational acceleration. So that's gravitational acceleration. We recognize it as G. Okay. Now, what we know is we learned in chapter 4 that the weight of an object, W, is given by mg. So we have mg, And we also know that that weight is a ramification of gravity. So that means it's actually equal to the gravitational force. So that's going to be big G times the little mass times the mass of the Earth, which we use that symbol for, divided by the radius of the Earth, again using that symbol, and it's going to be squared. Now, this is gravitational acceleration at the average radius of the Earth. Okay, you could call that at sea level, something like that. Now, what you immediately notice, hopefully, is that the mass of whatever body was experiencing the force that's called weight, that automatically cancels out, and we get what's left is G. So we can now say that G, gravitational acceleration, is equal to the universal gravitational constant G times the mass of the Earth divided by the radius of the Earth squared. So that is actually how you calculate the gravitational acceleration. And not only that, if you wanted to imagine digging a system of tunnels and stuff like that deep under the surface of the Earth, like at say half the radius of the Earth, then you could calculate what the gravitational acceleration is there by replacing the radius of the Earth with the radius of the Earth divided by 2. So that's another way of doing that. Now, with this in mind, let's calculate it and make sure it equals what we think it's going to equal. It's 6.67 times 10 to the negative 11th. That's Newton meters squared per kilogram squared. Then the mass of the Earth, we knew that was 5.98 times 10 to the 24th. Kilograms. Whoa, I really wrote that kind of small there. Let me write this a little bigger so everybody can actually read it. So 5.98 times 10 to the 24th kilograms. And then we're going to divide that by the square of the radius of the Earth. And I think the Earth's radius is 6.378 times 10 to the sixth. So 6.378 times 10 to the sixth meters. That quantity is going to be squared. And now I can do this calculation. Sorry about writing it so small, but you can see it there, 6.378 times 10 to the 6. So let's calculate it and see if we do get 9.80. We're going to say 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. Now I'm going to divide that by parenthesis 6.378 times 10 to the 6. That quantity is going to be squared, and that gives me 9.805. Uh, and if you look at the units, that turns out to be meters per second per second. And that's exactly what we expect. Of course, we only use 3 sig figs, so this 5 is not really correct there. Uh, and in fact, if we carried a couple more digits in the mass of the Earth and the gravitational constant, we actually might get a little closer to 9.80 instead of something that rounds to 9.81. But generally speaking, in our book, we do use 9.80. Anybody have any questions on that? Oh,
Kinda, but not in the generally just because I know 9.8 it's 9.8 meters per second squared. But generally when it's like um divided by something, why doesn't it become meters times second over second, leaving it just as meters then?
gotcha. So, that is part of the reason why I try to write it as meters per second slash second, just so you'll read it that way. But you can certainly call it meters per second squared because mathematically that's supposed to be it. What's going on here is that is a meter divided by a fraction. and the fraction is literally a fraction in the denominator. So if you wanted to actually, well, that doesn't really. Mm, I guess it might be better if I wrote it this way. Maybe this would seem a little bit more meters per second every second, because then it would make meters per second squared. So maybe that helps you a little bit more. Because in
Right.
actuality, the way I wrote it, meters per second, yeah, that turned out to be second on top, second on the bottom, and just meters. So nice catch on that. I think I've written that for a long time, and I thought I had thought it through once, but clearly I either didn't think it through or I just ignored it and kept going. But yeah, it should be meters per second and then a big slash second. That would actually work, because then if you divide by that second in the bottom, that's the same thing as multiplying by 1 over second, which would hit the denominator, not the numerator. So thanks for that, Colin. Appreciate it. Anybody have any questions? All right, your book does give a elevation and gravitational constants for various places. So, for instance, in New York, the gravitational acceleration is 9.803. The elevation is roughly zero. San Francisco is, again, the elevation is roughly zero, and that's 9.800. If you go up high, like the football stadium in Denver, that's an elevation of 1,650. Actually, that's a Mile High Stadium, and it's a little bit higher than 1650. But anyways, at 1650, the gravitational acceleration is 9.796. You can see that even at the highest altitude on Earth or the lowest distance below the surface of the Earth, the gravitational acceleration doesn't change by a huge amount. It's within a few percent in all cases. And that was the whole purpose of me assigning that extra credit problem, where you can calculate the G at the top of Mount Everest and then at the bottom of the Marianas Trench. So let's move on. Effect of Earth's rotation on G. This is example 6.5. So let me go there. Example 6.5 says effect of Earth's rotation on G. Assuming the Earth is a perfect sphere, determine how the Earth's rotation affects the value of G at the equator compared to the poles. So, uh, how is G affected at poles versus ooh, the equator? So what I'm going to do is I'm going to go ahead and draw a diagram to represent the Earth, and I'm going to try to make it a decent size Earth so that we can get a decent figure out of it. That looks pretty good. Okay, I'm going to say that this is the Earth's equator, and I'm going to say, notice I've got the poles sticking straight up when in reality the poles are actually tilted at about 23.5 degrees, but we're just focusing on the Earth at this point. What we're wanting to consider, though, is a person standing here at the equator versus a person standing here at the North Pole, and the South Pole by symmetry will be exactly the same result. So if I draw a free body diagram for this one, what's going to happen is this. I'm going to say this is my positive y-axis. It doesn't really matter which way I say is which, so as far as the x-axis goes, so I'm just going to put it there. It doesn't really matter too terribly much. I'm going to say the person has a mass given by m, and that the force acting on m points towards the center of the Earth, and that quantity is mg. and then there's a force acting on the person from the Earth, and that's the normal force. So it's going to point up this way, and that's F normal. But what you got to remember is in order for this person to actually stay on the surface of the earth, he or she is technically orbiting the earth around its axis, but at a distance of one earth radius. So you can imagine, for instance, this is the rotational axis, but the distance away is the earth radius. So this figure is not complete as it is. This figure also has to inform us that the acceleration is v squared over r, where v is the velocity that the Earth is rotating. So in this case, we'll say the Earth is rotating this way with some sort of velocity v at the equator. Well, what is that velocity? Well, we know that velocity basically goes the circumference of the Earth is the distance. So this person, if they sit perfectly still on the equator, this person would travel a distance equal to the circumference of the Earth, specifically at the Earth's equator, which is actually a little bit bigger. But the main thing is the distance they travel will be 2 pi times the radius of the Earth. And then that will be divided by the period of rotation of the Earth, which is about 24 hours. Now, I'll tell you that there's a difference between a sidereal day and a solar day, and we're ignoring that. So I'm just going to tell you that right now. So right now, I'm going to say that it's 2 pi times 5.98 times 10 to the, or excuse me, that was the mass. Oops, I was trying to write down the radius of the Earth, which is 6.378 times 10 to the 6 meters. Double check that's what I used earlier. Yeah, 6.378 times 10 to the 6 meters. Got that. And now I've got to divide that by 24 hours times 1 hour equals 3,600 seconds. So this will give us the velocity that a point on the Earth's equator is traveling. That's 2 times 3.14159 times 6.378 times 10 to the 6. Now I'm going to take all that and divide it by 24 times 3,600. Oops. For some reason, it didn't take my answer down, so I'm going to divide that number. And by the way, when I did the numerator, I got basically 40 million 74,122. So now I'm going to divide that 40,074,122. I'm going to divide that by 24 times 3,600 in parentheses. That gives me 463.8 meters per second as the tangential velocity of the Earth's equator. Okay, so now that means A, the centripetal acceleration would be v squared over r. That's going to be 463.8. Notice I did use one extra digit there, so I should underline that 8. That's meters per second, and then I'm dividing all this by 6.378 times 10 to the 6 meters. This 463.8 has to be squared, of course, so I'm going to take and square that, and now I'm going to divide it by parenthesis 6.378 times 10 to the 6, close parenthesis, and that gives me 0.03373 meters per second every second, which I'm writing as meters per second squared because what Colin brought up. So now that we have that, we can see that the Fn, which is really the force that a scale would have to apply to the human to keep the human from, sinking into the earth or lifting up off the earth. So if I take the summation of the forces in the y direction equals mass times acceleration in the y direction, what I'd get is Fn minus mg is equal to mv squared over r, so that the normal force, which is really the weight as measured by a scale, is really going to equal mv squared over r plus g. So in other words, we're adding a small quantity to that. And actually, let me double check the addition of that. The normal force is going to be, actually, it should be less. I don't know why I got a negative on that. Let me see. Mg is down. That's negative. Oh, the A was supposed to be in the negative direction. That's why. Sorry about that. So there should be a negative sign right here with the mv squared. So what we ultimately get for this particular part is F normal, which equals the weight of the scale at equator, is going to be equal to, I see another person's coming in. That's going to be equal to m times, instead of g, it's going to be g minus v squared over r, which I'm going to call m g prime, where g prime is like the gravitational acceleration at the equator. So g prime equals gravitational acceleration at equator. So in this case, g prime is going to be equal to 9.8 minus 0.03373. And that gives us 9.766, which is more digits than we have, than we really are allowed to have. So that's gravitational acceleration at the equator. G prime is about 9.76. If you did the same thing up here at the pole, then what you'd see is a y-axis pointing up, a mass m. We would have a weight mg pointing down. We would have a normal force Fn, which equals the weight of the scale, for instance. We'd have that pointing up, and no acceleration is happening. In fact, the acceleration is just around in a circle, so it won't hurt anything. In that case, the summation of the forces in the y direction equals mass times acceleration in the y direction, gives you 0, so that Fn is equal to, because it was Fn minus mg equals 0, Fn's just going to be mg there. So that's what happens between the gravitational acceleration at the pole, which should be roughly 9.8. It's technically a little bit less because the Earth, as a result of its rotation, it's what we call an oblate spheroid. So the Earth's equator is a little fatter than the other parts of it, sort of like, me. My belly is a little fatter around my midline, and the North Pole and the South Pole are actually a little bit smaller in radius. It's actually compressed downward. So you could actually get a slightly larger value of G at the North Pole and a slightly larger value of G at the South Pole, but that's not because of the rotation. That's a result of the Earth's polar radius from North Pole to the center, or from South Pole to the center of the Earth. That radius is a little smaller, so it's just like going to the bottom of the Marianas Trench, only not nearly as far. So, any questions on that? All right. So let's go on with other stuff. It looks like you guys are doing this okay. Let me check the chat, just see. It looks like everybody's already put in their first and last name, but I just want to make sure no one asked any questions, and that doesn't seem like that's happened. Now, what we want to talk about is orbits. Now, Newton actually wrote a book for layman's. So you can actually look. There's a book on the revolution of the orbs or something like that that Newton wrote. I'll actually look up the title for you if anybody's interested. But that actually explains gravitational forces and orbits and stuff like that. So I'm going to go over sort of that discussion of how an orbit occurs right now. So what I'm going to do first is I'm going to draw a picture of the Earth, and I'm going to try to draw it a decent size so that we can make a decent drawing. So there's the radius, or there's our picture of our Earth, if you will. Now, what Newton did is he imagined like a really big mountain. So let's imagine a really big mountain at the top, or we're looking at the Earth from, let's say, above the North Pole. So we're sort of looking at the equator, if you will. And let's imagine that we have a mountain like this on top of the Earth. Okay, it's sort of like that. Uh, like a 1970s sci-fi movie. I actually can't remember the name of that movie right now. But anyways, now what we're going to imagine is in addition to that, we're going to have a little cannon on top. And this stupid thing always fixing my drawings. It's aggravating. So here's a cannon, if you will, that's supposed to fire a cannonball. So what I mean by this, and I'm not really happy with that anyways. So there's my cannon. Like this. Okay. If you fire a cannonball from here, then it's going to fire and land. If you fire it a little faster, it's going to land a little further. If you fire it a little faster, it's going to land a little further. And in fact, if you fire it just right, it could, in principle, land right at the or excuse me, the diametrically opposed latitude from which you shot it. Okay. Now, if you give it just a little bit more speed, what will happen is that that particular cannonball would go out and get really, really close to the surface of the Earth at the opposite side, but then its velocity would continue it on so that it came back and ran if the resistance or if the air resistance of the atmosphere wasn't too terribly bad, it would basically just come back and hit the cannonball or the cannon in the very back of where it left. So that's sort of the argument that Newton was making, is that if you shot it at just the right speed, it would just barely miss the opposite side of the Earth. And what that tells us is when you just reach a fast enough speed to avoid hitting the Earth, then that is going to cause what we call an elliptical orbit, because the distance here from the center of the Earth to here, this orbit, is actually a little smaller than it is on this case. Okay? So this right here represents an elliptical orbit. Remember, a circular orbit would have the same radius everywhere. This one's got a smaller radius at the bottom than it does at the top, so it's an elliptical orbit. If you went faster still, then there's a point at which it would go like this and just stay the same height, at which time this becomes a circular orbit. If you went faster still, then it would go like this. And actually, in this case, it would go off a bit further on this side than it did on this side. And therefore, it would be an elliptical orbit again. In fact, what Newton was able to show mathematically is that the stable or the orbits that can happen from Newton's law of gravity are shapes called conic sections. And hopefully you knew this from your college algebra slash pre-calculus. But basically, imagine this scenario. You have one of those little paper cups like you sometimes see at gas stations. Imagine having one of those paper cups, and then at the bottom of that paper cup, we're going to have another paper cup. And in fact, we can imagine the paper cups going on for infinity. And what we do then is we say, we can imagine all the ways that you can slice through this double ended water cup, if you will, and each of those will give a shape of what we call a conic section. So if I were, for instance, to slice along perpendicular to this symmetry axis. Notice this purple line's the symmetry axis, meaning I can rotate this conic section by any angle I want and it'll look exactly the same. So it's a symmetry axis, and in fact, it's a continuous symmetry axis. Now, if I make a slice perpendicular to that, then obviously this looks like an ellipse, but technically what's going to happen is it will be, in fact, a circle. Okay, so that's one of the conic sections is a circle. Now, if I chose to slice across this cup, not perpendicular to the symmetry axis, but at some angle to it that's smaller than the angle that the side of the cup makes, then I get a different shape, and that shape would be like this. And this angle is significantly different from 90 degrees. This is an ellipse. Now, if I also wish to take a slice, let's say parallel to the axis, then what I would get is this shape here, and I would also get a very similar shape on the other side. These two guys are called hyperbolas. Well, actually, they make a hyperbola, and the hyperbola actually has two parts. Okay. Now, you could also make a cut that's parallel to the sides of the cone. And when you did that, what you trace out is a shape called a parabola. So those are actually all the types of orbits you can get from Newton's law of gravity, which is a 1 over r squared law. So Newton was able to show that as well. And that's the conic sections. So that is actually how he explains the orbit. And as I hinted to you earlier, using Newton's second law, the summation of forces is equal to mass times acceleration. This actually gives us g times the mass of the orbiting body times big M, the mass of the body being orbited, divided by, if we choose to use A for the semi-major axis instead of R for the radius, we could put an A in here, but I'm going to put an R squared instead. And that's equal to mv squared over R. And hopefully you remember that this is what I did last time. and it was what allowed me to derive Kepler's third law, basically. So that's one of the extra credits you can do. You just have to go ahead and take V equal to 2 pi r over the period. And then, like I said, you need to assume that the orbit's actually circular, and instead of calling the radius r, call it a, and boom, out will pop Kepler's third law. So that's really the equation that dictates orbits, is this GMM over r squared is equal to mv squared over r. There's a little bit of change for it in the event that the orbit is not circular. Uh, the solution is a little bit more complicated, but you basically get the same thing. But also, if you had one object orbiting another object and the two objects were, closer to the same mass, then what you'd ultimately get is two objects orbiting a common center of mass for the system. And in that case, you'd have to sort of write out a F equals ma for one mass, a F equals ma for the other mass, and you'd still get Kepler's third law applied. But anyways, uh, that's the crux of the matter regarding orbits. Anybody have any questions on that? All right, let's look at example 6.6 then. This is example 6.6, and it says geostationary satellite. A geostationary satellite is one that stays above the same point on Earth, which is possible only if it is above a point on the equator. Why? Because the center of a satellite orbit is always the center of the Earth, so it is not possible to have a satellite orbiting above a fixed point on the Earth at any latitude other than 0 degrees. Geostationary satellites are commonly used for TV and radio transmission, for weather forecasting, as well as communication relays. Determine A, the height above the Earth's surface such a satellite must orbit, and B, such a satellite's speed, and C, compare the speed of a satellite orbiting 200 kilometers above Earth's surface. So they want to know the height, and they want to know the speed, and then they want to know how that speed compares to something just orbiting 200 kilometers above the Earth's surface. So let's do that. What we know is the mass of the Earth is equal to 5.98 times 10 to the 24th kilograms. We're going to say the mass of the satellite is just m sat. That's going to cancel out anyways. Uh, I'll just leave it as that, but we're not asking for it. I just put a question mark by it to say we don't know what it is. There's the mass of the Earth. What we want, though, is the period of the orbit to be 24 hours. Okay, so that's what's going to dictate it being a geostationary orbit. So when I do this, I'm going to say, using Newton's second law, the summation forces is equal to mass times acceleration. It is a vector equation, but we're dealing with it here in a single one-dimensional sort of scenario, because we're looking at the Earth like this. There's the equator, and we're looking at a body right here of mass m satellite like that, and this object is going in an orbit whose radius I'm going to say is big R, and that equals question mark. But more specifically, we want to know H. That's the question that we were asked for. And we also want to know V equals question mark. So doing this with Newton's second law, I'm going to say G times the mass of the satellite times the mass of the Earth divided by r, the orbital radius, squared, is equal to m, the mass of the satellite, times v squared over r. Again, we can see that this r is going to cancel out with that. This msat is going to cancel out with that as well. But what we also need is v is equal to 2 pi times that big radius. divided by period, and we can put that in. That's going to give us G, mass of the Earth, over R is equal to 4 pi squared R squared over T squared. So we can finally solve for R cubed by saying R cubed is equal to G M, and then that's going to be divided by 4 pi squared and then T squared on the top. So that means R is equal to the cube root of 6.67 times 10 to the negative 11 times the mass of the Earth, that's 5.98 times 10 to the 24th kilograms, divided by 4 pi squared, and then 24 hours times 3,600 seconds per hour squared, all that under the cube root power, or under the cube root. So now we can compute all that. I'm going to write it down. I get the cube root of 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th uh, times 24 times 3,600 times 24 times 3,600, and then I'm going to divide all that by 4 times 3.14159 times 3.14159, and all of this gives me the cube root of 7.452 times 10 to the 22. Now I'm going to take the cube root of that. That's the same thing as raising it to the 0.33333 power. And that gives me 4.225 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th meters, and that's one extra sig fig. Now I have to subtract from that the radius of the Earth to get h. So h is equal to 4.225 times 10 to the 7th meters minus 6.378 times 10 to the 6th meters. And that gives me 3.587 times 10 to the 7th, I believe, 1, 2, 3, 4, 5, 6, times 10 to the 7th meters. So that's the actual h, that's the height. And of course, now you can also figure out what the velocity is. The velocity is 2 times 3.14159 times r, which is 4.225 times 10 to the 7th. And now I'm going to divide that by parentheses 24 times 3,600, close parentheses. That means 3,072, or actually 3,073 meters per second. That's good enough. We could do the same calculation for uh, R being 200 kilometers plus the radius of the Earth, because that's what they mean when they do the H. And you can do that, but we've run out of time, and I think this is sufficient. We've also covered what I think is enough of Chapter 6. So we're going to go on to Chapter 7 next time. I'll post more videos, or I'll publish more videos in this week's module, so you'll have other examples to look at. But we're done with Chapter 6. Uh, I'll wait here for the last person to leave in case anybody has any questions, but you're all free to go. Just don't forget to chat me your first and last name. Thank you. You too, Sawyer.
I have a quick question about the chapter 6 homework.
Yeah, no, go for it.
So on Pearson, it says, I think it says it's due the 19th, and then on Canvas, it says it's due on Sunday.
I
So I was
thought I
just
mentioned
wondering.
something about that on my syllabus. I might not have, but I tried to mention it in class. Canvas sometimes spits in due dates, so never, ever, ever trust the due dates for any mastering physics stuff as seen on Canvas. It's really whatever's listed on the My Lab and mastering side. If you're saying it's due on the 19th from the mastering side, then that's a safer bet for you. Let me pull it up real quick and see what it is for chapter 6 in your class. I've got the homework due 10/19. Yeah, that's actually quite a bit further than it's supposed to be. It really should be due on this Saturday or this Sunday, but I'm going to give you till Wednesday just because I've been saying it's 10/19 for so long. So let me go ahead and change that date while everybody can see that I'm doing it. I'm changing the conceptual. I'll leave the conceptual for the 12th, but I'm going to change the homework for the 21st. That way you guys can have it done before Wednesday. And it's set now. So it's not 21st. Sorry. It's not supposed to be the 21st. It is supposed to be the 14th. Sorry about that. So to now have it set, the conceptual homework's due 10/12 and the homework for chapter 6 is due 10/14.
All right, perfect. Thank you. I appreciate it.
No problem. Let me know if that's too tight because I know I did change it last minute. So if anybody has any problems meeting that, I'd be willing to at least push it till Friday if necessary. Thank you, everybody. Anybody else have any questions?
Yeah, I had a quick question about the test.
Okay, go for it,
Yeah,
Melanie.
I have it set to do it at the testing center on Friday. That's still fine, right? Because I remember you sent an
Yes.
email saying that yeah.
Yeah, I
Okay.
moved it and basically made it even available up through Saturday. And I did let the
Okay.
testing center know, so they should be able to accommodate that.
Okay, perfect. I was just making sure.
All right. Try not to speak with and other people, if you've already taken it, try not to speak with other students about it because right now there is some similarities between whatever people are taking online versus whatever people are taking face to face. Well, I
Mhm.
say online at testing centers. So you're actually giving other people an advantage if you talk to them about it. And of course, that could cause a problem in that the rounding whenever I decide to curve a test. If more students do well on it, there's less likely for anybody to get a curve. So just be careful of that.
Okay,
Thanks,
will
Melanie.
do.
That
Of
wasn't
course,
for you, of course. That was for other people, but
you're
thank you.
you're good.
All right. Have a
I
good one, Melanie.
understand. Have a good weekend.
You too. David, Colin, either of you guys have any questions?
Yeah, I was actually I just wanted to ask if there was going to be a curve just because I yeah, you know.
Yeah. So normally, like I said, this first test can be quite low. But that was when I was grading it as a multiple choice with no chance for partial credit. I'm thinking once I grade it with partial credit, it's going to be a little bit higher average. And if the average is really, really low, sometimes I do curve it, but not always. I usually just I like to keep a little bit of pressure on students because what I find is they're much more likely to become complacent if their grades are good. So I'd rather them be a little on the anxious side, even though I tell them, hey, I'm going to do everything I can to make sure that y'all are not only passing, but that you're successful. You're getting A's and B's, that kind of thing. So I probably will
Okay.
not round it, but that could happen.
Okay. All
I'll
right.
I'll let you know. Like I said, once I get it all graded, I'll give you an idea about whether I curve it or anything. So you'll know whether or not it's been curved once I put the
All
grade.
right.
All right,
Okay.
you'll
Yep.
do fine.
Thanks.
Don't worry, Colin. I got you. How about you, David? You have anything, sir? All right. Well, I am going to call it a day. I am exhausted. So thanks for coming, everyone. I hope you have a wonderful night and a wonderful weekend. Stay safe, and I will see you guys next week. Remember, we have homework. You should try to get it done this Sunday. That would be smarter of you. But like I said, I made the conceptual questions due by Sunday, but the actual homework for chapter 6 is not due till Wednesday, or excuse me, till Tuesday night on the 14th. So y'all have a good one, everybody. Bye bye.